So in this video, we're going to introduce the concept of entropy and discuss how entropy is related to spontaneity and spontaneous processes and non-spontaneous processes. First, a little refresher. What have we learned about spontaneous processes so far? We've learned that spontaneous processes are what's called thermodynamically favored. Okay? Which means that, according to the energy calculations, the reaction should happen without any extra assistance, besides the activation energy that's needed. This is usually true for exothermic reactions. Usually, exothermic reactions are spontaneous. Remember, another little refresher, if a reaction is spontaneous in the forward direction, that means it's going to be non-spontaneous in the reverse direction, and vice versa. Now, most spontaneous reactions are exothermic, but not all of them are. In fact, you can have spontaneous processes that are endothermic, which we're going to get to in a second. But one thing that I also want to point out, when we think of spontaneous, we usually think of something just happening. And usually when we say just happening, we think really quickly or fast. But spontaneity does not tell us about speed of a reaction. It doesn't tell us about anything about how fast a reaction will go. That's kinetics, rate laws, rate orders, mechanisms, and everything. Okay? All that it tells us, all that spontaneity tells us is whether or not a reaction will happen or what direction it will happen, forward or reverse. Small example of this, okay? Carbon, okay, solid, turns into carbon diamond. If you have enough pressure, so at high temp and pressure. However, that doesn't happen very fast. That process takes millions and millions of years, even though it's spontaneous. This is a spontaneous process. It's just very, very slow. On the other hand, you light a hydrogen balloon, like the Hindenburg, boom, that's a very fast process that's also spontaneous. So spontaneity doesn't tell us anything about speed. If we think about ice, okay, H2O solid, okay, turning into H2O liquid, you put an ice cube out on a table, it's just going to start to melt. This is spontaneous, okay? But if you measure the enthalpy change of this process, it's positive. Delta H is greater than 0, which is endothermic. And that's kind of counter to what we've been learning. Most spontaneous processes are exothermic. This one is endo. Why? What makes something spontaneous even if it's endothermic? Well, that thing is called entropy. E-N-T-R-O-P-Y. Entropy. What do we need to know about entropy? Okay? There are two things. We can measure it. Okay? The letter that's used is a capital S. Or when we're measuring changes in entropy, delta S. S is used for entropy. Capital E is already used for energy, so we got to use a different letter. Okay? The units of entropy are joules per Kelvin. Okay? And that's something to watch out for. Okay? The fact that this is in joules, okay? Because most things that we've been measuring related to energy are in kilojoules, like delta H is in kilojoules per mole, okay? More specific, and we'll find about Gibbs later, but you got to know that entropy is joules per Kelvin, okay? What do we need to know about entropy? Where does it come from? Well, it comes from something called the first law of thermodynamics. There's 3 laws of thermodynamics that we need to know. The first law of thermo, okay, sometimes abbreviated just thermo, is that energy in a reaction is always conserved. Okay? Whatever energy you start with, you have to end with. However, energy can change forms. Can change forms. So for example, you can have chemical energy. You can have thermal energy. You can have kinetic. You can have potential. These are all terms that you've learned in your science classes of different types of energy. The cool thing about energy, you can change forms. You can have energy go from thermal to chemical, or thermal to kinetic, or thermal to potential, or potential to kinetic. It can change. An example would be a solar panel. Okay? A solar panel takes energy from the sun, which is thermal, and converts it into electrical energy, okay, to power a light bulb. Okay? The way that we can measure how much energy can be changed is entropy. Okay? So entropy is a measure of how energy can change forms, how much energy can change forms. Okay? More specifically, okay, entropy is really a measure of disorder. Okay? Or it's a measure of chaos, a measure of organization. Okay? So more entropy, a system or a reaction that has more entropy, means that there are more ways to change forms for the molecules, or more ways for the molecules to change the energy that they have. Another way of saying that is that there's more disorder. More entropy means more disorder, which another way of saying is more like unorganization, which is not really a word, but it's going to work for now. Whereas systems that have less entropy, okay, they have fewer ways to change form. Okay? Or another way of thinking about it is that they are more organized. They are less chaotic. There's less disorder. So that's the main thing that's a need to know for energy, kind of in our own words. It's a measure of how organized stuff is. The more unorganized stuff is, the more entropy it has. So just think about some common examples. Let's say you're in a room and someone sprays some perfume. They start with that perfume out in the corner where it gets spread. Eventually, over time, that perfume is going to spread all the way throughout the room. Okay? The entropy, meaning the measure of organization, is going to increase. Entropy, S, is going to increase as that perfume spreads out. Ice melting. Let's reconnect back to our old example. You have a solid ice cube. It's nice and organized. As it melts, it turns into a puddle of liquid water. This is also an increase in entropy. And that causes, since there's more entropy, since the entropy is increasing, that means the molecules are more unorganized. They're more disordered. They're more spread out. This comes into the form of something called the second law of thermodynamics, which means for a spontaneous reaction, the entropy of the universe is always going to be greater than zero, or the change in entropy is going to be greater than zero. So for any reaction that's spontaneous, which is thermodynamically favored, the entropy will increase. So entropy will increase if reaction is spontaneous. So that means the molecules will be more spread out. There will be more ways for them to change forms. They are more unorganized. So here's another non-chemical example. You're standing right here in the middle and you have a pile of bricks. You throw the bricks into the air. There's two possibilities. The bricks could fall into a nice organized pattern here and make a nice brick wall. Or maybe they fall just into a big old pile like this. Let's think about which is more likely to happen. Well, it's much more likely, much more probable that they're going to be in a very unorganized state. Okay? Unorganized means more entropy. On the other hand, over here, this is very organized. Okay, it's very neat. This has less entropy. So thermodynamically speaking, which of these is more likely to happen? The one that's more likely to happen is the one where the entropy will increase. In this case, this process is much more likely to happen than this one. In fact, the one on the left will probably never happen. Okay. This is the second law of thermodynamics as an equation. This is kind of it in words. Entropy will increase if a reaction is spontaneous. Okay. A chemical example is, let's say you have two solutions mixed up together, two different solutes. Here we have green solute and yellow solute. If they start in this particular position and you let them just mix and float around and move in random directions, maybe after 10 minutes, it looks like this, even though you're not doing anything. Since you're not adding anything to the molecules, that makes this reaction spontaneous or thermodynamically favored. Well, now let's make that argument in terms of entropy. Well, over here, this is very organized. The molecules are in a very particular arrangement. The green one's on top, the yellow one's on the bottom. Over here, very unorganized. The molecules are all spread out all over the place. You have yellow ones in some places, greens in others. So this has more entropy, more S. Okay? So, and again, we can argue that this is spontaneous because entropy is increasing. In this direction, it's spontaneous, entropy is increasing. And the other direction, that would be non-spontaneous because the entropy would be decreasing because you're moving to a more organized state. Last but not least comes the third law of thermodynamics, which we're going to get a lot of practice with next in our next lesson. But what you need to know is if we want to measure entropy, we have to have a zero. We have to have a standard. Okay? So the entropy, S, of a compound, okay, at absolute zero, if you remember absolute zero, that's 0 Kelvin, okay, is 0. So if you want to measure the entropy of a compound, it's 0 when the molecule is at absolute zero, at 0 Kelvin. Since we can set that to our 0, we can then measure the entropy of any compound that's not at absolute 0, which makes our lives a lot easier when we do calculations involving changes in entropy, which we will do in the next class. Okay? So, if we put it all together, if we want to measure, you're thinking, wait, how do I know if the entropy is actually increasing? Okay? Well, increasing entropy, that means you're increasing disorder, okay? Which means you're making things less organized. Well, how can you make things less organized? Well, you can increase the volume. So if you make, you have two molecules here in a small box versus two molecules here in a big box, there's so much more room for them to move around. There's more opportunity for them to be spread out and disordered. So this has more entropy. What else could you do? You could change the phase. Okay. So for example, a solid where the molecules are all compact and close together versus a liquid when they're spread out. Again, more spread out, more opportunities for these molecules to move around. This has more entropy. You could change the concentration. Okay? Change concentration. So by having 2 molecules versus having 4, okay, there's more molecules in the second box. There's more opportunities for them to move around, more combinations that you can make, more entropy. Okay, you could also change the number of moles. Okay, the number of moles or molecules or atoms. Okay, which is the same idea as up here. If you're doing a chemical reaction where you go from 1 mole to 2 moles. You've made more molecules, you've increased the entropy of the system. There are more examples that we'll talk about, but these are a few that you need to know. You need to be able to walk away with an understanding of the 3 laws of thermodynamics, third law, second law, first law, and your need to knows about entropy.